Okay. All right. Like to welcome everyone to the Venus Surface and Atmosphere Conference afternoon session on Venus volcanism. Let me just mention how thrilled I am to be. I always like to travel, and yes, I am traveling to my home institution. It's a long story, but I especially love to travel for a Venus focused conference. This is the energy here is just great, and I hope you all are enjoying it as well. I'm going to, without further ado, I'll introduce the first talk by Hahn and Byrne, which is Spatial Patterns Analysis of Volcanoes on Venus.
Hey everyone, can y'all hear me okay?
I can hear you.
Good.
Yes.
Okay, awesome. Thank you. Hi everyone, my name is Becca Hahn. I'm a PhD student at WashU in St. Louis, and I work with Paul Byrne. And today I'm going to be sharing with you a little bit of the work we've done regarding spatial pattern analysis for volcanoes on Venus. Next slide, please. Thank you. So before we get started, I just want to share with you all our global catalog of volcanoes on Venus. This data set includes about 85,000 structures, 98% of which are less than 5 kilometers in diameter. And I will say this data set is available online now. So if it's available at the WashU data repository. So if you just Google my name and Paul's name, and then WashU data repository and Venus volcanoes, it should pop up. We're already on version 2, so I recommend using that one, and you can download it as, it'll download as a shape file or a CSV file. And so as you can see, just with this data set, these volcanoes are geographically widespread. Next slide, please. So with this data set, we wanted to use this kind of as a tool to better understand how volcanoes are distributed across the planet, why we see certain sized volcanoes in certain places, and what that can tell us about the underlying magma sources that are supplying or once supplied these volcanoes. Next slide, please. Thank you. So before we got into the spatial analysis, we really wanted to take a moment to look at the size frequency distribution of these volcanoes. So for all the volcanoes in our catalog greater than 5 kilometers in diameter, we have a calculation of the mean diameter. And there's about 850 volcanoes that we have the diameter for. So we tested a power law and an exponential distribution. And we found that neither model fit the entire data set well. So we opted to use a mixture model, which if you're not familiar with that, mixture modeling is a statistical method for basically identifying subpopulations within your overall population. So we used MATLAB to basically identify these two different distributions within our data set, and it's kind of divided by this diameter threshold of 63 kilometers. So if you would hit next slide twice for me, I just have some arrows, and then one more time, thank you. So the top plot A, this is showing our distribution of volcanoes that are greater than 63 kilometers in diameter, and both of these distributions are exponential. And if you look in the map on the left-hand side, we have the kind of spread of those volcanoes that are greater than 63 kilometers in diameter, shown as orange triangles. And likewise, we have those volcanoes that are less than or equal to 63 kilometers in diameter, shown in plot B, that's the distribution. And then in the map on the left-hand side, those are shown by those teal smaller triangles. So we basically used the results of our mixture modeling approach to kind of continue on with our spatial analysis using these two subpopulation distributions that were identified in this mixture model. Next slide, please. Thank you. So the type of spatial analysis we performed is called kernel density analysis or kernel density estimation. This is a non-parametric statistical approach for estimating spatial density using existing point locations. So in our case, we're using the locations of these volcanoes. So here on the left-hand side, this map is showing our volcanoes that are greater than 63 kilometers in diameter, the locations of those volcanoes. And then if you'd press next slide twice for me, please. And then, so here on the right-hand side, we have our map following our kernel density analysis. And here we're showing the spatial density of these volcanoes that are greater than 63 kilometers in diameter. And sort of the main takeaway from this is the darkest pink regions are the regions of highest volcano spatial density for volcanoes of this size range. And the spatial density is decreasing as you get into those sort of lighter pink colors. Next slide, please. Thank you. So if you're familiar with kernel density estimation or kernel density analysis, it's been widely used to look at the spatial distribution of volcanoes on Earth, as well as craters on other planets. One of the sort of driving parts of this type of analysis is what's called the bandwidth or the smoothing parameter. And the value selected for the smoothing parameter really influences your resulting map. So for example, if you pick a really large value for this bandwidth parameter, you might end up over smoothing. Your final map might be over smooth and you might miss certain features of importance. Similarly, if you pick a really low bandwidth value, you might
Is Loki?
under smooth your your resulting map.
Please be sure, sorry, external,
Oh, you're fine, you're fine.
other people, please mute yourselves. Thank you.
Thank you. You might under smooth, and you might maybe pick up on noise in your data set. So what we did was we employed an optimized bandwidth algorithm called, I've been calling it SAMSI, but it's an acronym for sum of the asymptotic mean square error. This is a data-driven approach to identifying the ideal bandwidth value for creating your kernel density maps. So we tested several other different types of optimized bandwidth algorithms, but here I'm just going to focus on the results of this algorithm. And on the left-hand side, we have our spatial density map for volcanoes greater than 63 kilometers in diameter. And on the right-hand side, we have that spatial density map for those volcanoes that are less than or equal to 63 kilometers in diameter. And like the map I showed on the last slide, in this map, the dark teal areas are the area of highest volcano spatial density, and then it sort of decreases as you get into those lighter blues. Next slide, please, or just click. Thank you. So here in particular, I want to focus on these high volcano spatial density regions. And I apologize in advance. I'm going to say high volcano spatial density region 1,000 more times. So these are the regions where we see the highest concentrations of volcanoes. So on the left-hand side, it's shown in that, on the left map, it's shown in that pink region. And then well, just on this map, it's shown as the orange colors are the volcanoes that are less than or equal to 63 kilometers in diameter. So here on this slide, we wanted to look at these high volcano spatial density regions in conjunction with geophysical data sets. So the background map is the mean crustal thickness map that was developed by James et al. And what we did was we basically used these high volcano spatial density boundaries to extract the pixels within these regions. So the histogram, or the histogram on the bottom, shows the spread or the distribution of crustal thickness values for volcanoes that are greater than 63 kilometers in diameter in pink, and those that are less than 63 kilometers in diameter in orange. And if you would click twice for me. Thank you. So ultimately what we found was that for those larger volcanoes greater than 63 kilometers in diameter, we found an average crustal thickness value of about 15 kilometers associated with that region. And for those smaller volcanoes, those less than or equal to 63 kilometers in diameter, we found an average crustal thickness of 13.5 kilometers for the volcanoes sort of in those distributed regions. Next slide, please. So in conjunction with looking at geophysical data sets, we also wanted to compare these high volcano spatial density regions with proximal tectonic and volcanic structures. So here we've also included large volcanoes from our global catalog, as well as coronae from Ivanhoe and Head 2011, as well as the locations of the Beta Atlathymus region. And if you click once for me, please. For that pink region, the high volcano spatial density region for volcanoes greater than 63 kilometers in diameter, you'll notice that that region almost perfectly aligns with the boundaries of the Beta Atlathymus region, which is a region well documented for having possible mantle upwellings. And we also note that this region contains many large volcanoes, 32 volcanoes greater than 100 kilometers in diameter, and almost 160 coronae. And then if you click one more time for me. Thank you. We repeated this process with the distributed regions of high volcano spatial density for volcanoes less than or equal to 63 kilometers in diameter. And of those 14 different regions, those 14 different sort of orange outlines, we found that 4 associated with the BAT region, at least 7 of them contain or are within 50 kilometers of at least one large volcano, and 11 of them contain at least one coronae, with several containing upwards of 10. Next slide, please. So we wanted to kind of use those results that we found with the geophysical data sets, as well as the proximal tectonic and volcanic structures, and kind of interpret what that might mean for volcanism in these different regions. So first, we're going to focus on the volcanoes that are greater than 63 kilometers in diameter. And if you click for me once, please. We note that the high volcanospatial density region is perfectly aligned with the BAT region, and volcanoes in this region are probably fed from shallow magma reservoirs that originate from a deep-seated source, which is probably unsurprising to many of you, knowing sort of what the volcanism in the BAT region. And then if you click one more time. We also find several volcanoes, large volcanoes outside of the BAT region. These could have formed as a result of a shallow melt source that produced a large quantity of magma, or these volcanoes could be the product of a thermally relaxed older upwelling. Next slide, please. Likewise, we did this with the smaller volcanoes. So if you click one more time. We noted that many of these volcanoes are proximal to large volcanoes in coronae, and this could be as a result of a waning magma supply to those larger edifices or the coronae, which led to the formation of these smaller volcanoes. Many of them surround or on the flanks of these edifices, similar to how we see Mauna Kea or Mount Etna here on Earth. You click again. We also find some of these high volcanospatial density regions are completely isolated from large volcanoes and coronae. These could be just the products of comparatively lower magma supply rates that weren't producing enough to generate a larger volcano, and instead produce these smaller volcanoes. And then one more click. And then you also might notice that several of these high volcanospatial density regions are proximal to rift zones, particularly within or near the BAT region. And these could be products of dike emplacement associated with those extensional stresses in those areas. And then one more click. One more, sorry. So in conclusion, we find that generally the high volcanospatial density regions for those volcanoes greater than 63 kilometers in diameter is very well aligned with the Beta Atlathemus region, and they're probably associated with the inferred upwellings in that region. The 14 regions of high volcanospatial density for those smaller edifices may reflect localized differences in the magma supply and ascent in each of those regions. Some, like those that are in the BAT region, could be linked to mantle upwellings, whereas others could be the manifestations of a melt anomaly. And then one more click and I'll be done. And then in the future, we're going to kind of be zooming in. Instead of looking at these structures on a global scale, we're going to look at these high volcanospatial density regions on a regional and local scale to better understand the shape of the magma source. Thank you. If you have any questions, please email me.